Hi everyone, today we are going to talk about the application of in-situ X-ray diffraction in structural transformation of cathode materials for lithium-ion batteries. We'll introduce this to you in 3 parts. Let's start from introduction. First, we'll talk about some basic knowledge of lithium-ion batteries, and next we'll talk about in-situ X-ray technology. Finally, we'll give a brief introduction of the cathode materials that we'll use as an example in the following sections.
Currently, due to the growing severe air pollution and climate change, lithium-ion batteries have been widely used for energy storage around the world. They are the main power source for EV vehicles, or as we call it, electric vehicles, due to their relatively mature technology and excellent performance. And they are also a threshold for driving EVs to occupy the vehicle market. The basic principle for lithium-ion batteries are the insertion and the extraction of lithium ions. During the charging process, lithium ions extract from cathode materials, passing through the electrolyte and insert into anodes, where they are stored. While in the discharging process, lithium ions behave in the opposite way, returning to cathode and thus provide energy for electric equipments. Apparently, since lithium ions continuously insert and extract from electrodes during charge and discharge cycle, complex reactions might occur, such as electrode degradation, phase transitions, and reactions at the electrode or electrolyte interface, which have negative impact on the final energy density and working life in practical applications. Thus, it is important for us to find out what happened inside the batteries during the cycling process. in-situ XRD helps us solve the problem. In-situ refers to the analysis in a specific site of the sample within the native environment of the battery, which means it can help us record the composition and structural transformation during the cycling process in a sealed battery cell. Without opening and disassembling process, this greatly reduces the risk of contamination or relaxation of metastable species. Thus, the data collected is much more accurate and close to real conditions. Figure on the right shows the model of designed coin cells and pouch cells for in-situ XRT. It's almost the same as not as the normal cells, except that one hole for reflection mode and two holes for transmission mode are covered with X-ray transparent materials, such as Kapton film used in this model. They are usually made on in situ or open the cells as windows. This allows the X-rays to reach the sample region and the detector, which provides us detailed information inside the cell. The nickel-rich layered cathode is a promising future cathode material for lithium-ion batteries in electrical vehicle due to its high specific energy density. We will take lithium nickel manganese cobalt oxide as an example in the following discussion. Besides, it can offer substantially higher practical capacities than conventional lithium cobalt oxide at a lower voltage. They also require a substantially lower amount of the more costly mineral cobalt. However, the severe problem for nickel-rich cathodes is they exhibit fast voltage and capacity fading. Since batteries' material redox potential, capacity, and cycle life are strongly related to the evolution of their structural properties during the electrochemical reaction. The advanced in-situ XRD technology can provide us new insights into the structural changes and lithium dynamics of lithium nickel manganese cobalt oxide during the electrochemical charge and discharge, which are essential for a better understanding of its fast degradation.
Next, in the discussion part, we'll take MC811 as an example to illustrate how we can use in-situ XRD to probe the detailed information of cathode materials during cycling. In sequence, we will analyze powder XRD pattern, in-situ XRD pattern with voltage profile, and lattice parameters evolution plots from XRD refinement.
The figure A shows the X-ray diffraction pattern of the initial materials NMC A11. All peaks are indexed by the structure of alpha sodium ferrite with the R3M space group. Noticeable separation of WX 006012 and 018110 indicates the layer structure of the material. The in-density ratio 003104 is 2.29, indicating low level of cationic mixing and accordingly the ordered structure of the cathode material. The effect of lattice perimeters, slight change in the in-situ assembly compared to the initial powder was observed. The noticeable decrease in the intensity of the peak 003 relative to the others can be explained by the influence of the irradiation angle on the depth of X-ray penetration. F the figure is in-situ XRD pattern during the first two cycles. By refinement from the in-situ XRD pattern, the evolution of A and C lattice parameters is plotted. According to the in-situ XRD, peaks are almost at the same position as the powder XRD mentioned before, remaining lower structured. However, no monotonic displacement of the peak 003 during the charge indicates a nonlinear change of the parameter. Parameter A, in contrast, continuously decreases since peak 110 constantly shifts to the right. Considering corresponding voltage and electrochemical behaviors, we can explain why A and C changes like this. At the first stage, the charge star lithium ions de-intercalate from the structure of the cathode material, so the electrostatic repulsion forces between the oxygen layers increase, thus parameter C increase. Thus the charge compensation passes with the oxidation of the transition metals. Parameter A decreases at the second stage. Parameter C falls rapidly. This can be explained by cation mixing of nickel and lithium ion due to their similar ion radius. In addition, the structure of the cathode material begins to release oxygen ions, so the repulsion of oxygen layers decreases at the third stage. The parameter A doesn't change, so the charge compensation no longer presses with oxidation of transition metals, but only with the release of lithium and oxygen. Parameter C continues to decrease for the same reason as in the second stage. The first stage matches the beginning of the discharge. Parameter A gradually increases throughout the charge due to reduction of transition metals. Parameter C increases since lithium ions stabilize the structure by filling the vacancies of transition metals. At the fifth stage, the nickel vacancies are filled, so lithium intercalates only in the lithium layers, so the electrostatic repulsion of oxygen loss decreases as well as parameter C.
Figure on the left shows the volume changes of the unit cell NMC and the C/A ratio depending on the charge potential. Due to the release of oxygen at charge above 4.2 volt, rapid compression of the crystal lattice, and noticeable decrease in the C/A ratio leads to mechanical tension in the unit cell. which can cause deformation of cathode structure. These anisotropic lattice expansions are expected to lead to strain within particles, which can eventually cause particle cracking after prolonged cycling. However, the choice of comparably low cutoff voltage also reduces the available capacity, removing one of the advantages of using AMC-811. As a result, the future studies will focus on the role of cation and nickel defects in the lithium layers on lithium mobilities and C parameter changes. There are also other deep research that we can also have a closer look at the evolution of interlayer spacing, which reveals that the lithium and transition metal layers behave differently as the C lattice parameter increases. The lithium layer expands, whereas the thickness of the transition metal layer decreases. The latter is caused by the decrease in the ionic radius of nickel ions and the increased covalency of nickel-oxygen bonds with increasing charge of the nickel ions. The subsequent decrease of the C lattice parameter is initially caused by further contraction of the TM layer, which is then followed by the collapse of the lithium layer. In this presentation, we take AMC-811 as an example, analyze the in-situ XRD pattern and corresponding refinements of cycling battery cells. Related to the lattice parameters evolution to the charge-discharge behavior, we explore the reasons why the lattice constants A and C change in 5 stages. It is considered that the mechanical tension at high voltages is the main reason for structural degradation. However, it's really a complex process that needs more discussion. But this do demonstrates that in-situ XRD is really a useful tool in lithium-ion batteries research. That's all for today's presentation. Thanks for listening.